Hello everyone! In this video we will continue to examine topic 5.1 electric fields. And in particular we will take a look at calculating the electric field from more than one charge and a few example problems. The first example problem I'm going to discuss is this example problem, example 20.8, finding the field near a dipole. So this is our charge distribution, and we're asked for the field at this point. Notice, and this is sort of key to understand, we're not using Coulomb's law to discuss the interaction between this charge and this charge. We're asking ourselves, what would the field be at this point? And that point right there, okay, if we put a charge there, would produce a force. And that force would be due to both of this, both the negative charge and the positive charge. But our field question is really like, what is going on in that space? There's no charge there. We want to know what this charge and this charge is doing to the space right there when we're calculating the electric field. So to do that, we use the principle of superposition and we say, okay, well, the electric field at this point will be due to the electric field from this positive charge and due to the electric field from this negative charge. Let us consider, before we do any calculation, what direction we would expect it in. Well, the electric field due to this positive charge will be away, okay, with a particular value. And that's because, remember that the electric field direction is the same direction as would be on a small positive test charge placed right at that point, okay? And that would be repulsion, so the electric field would be going away. This negative charge, though, will be attracting, or would attract, a small positive test charge placed at this point, and so the negative charge will contribute a small portion of the electric field that's to the left in the opposite direction. On the other hand, the portion of the electric field from the positive charge will be significantly bigger than the portion of the electric field from the negative charge, because the portion of the electric field from the positive charge is 1.2 centimeters away from the positive charge, and from the negative charge, that point is 2.4 centimeters away. So our final diagram looks something like this. The electric field from the positive charge is big and away. The electric field from the negative charge is towards and to the left. And the resultant electric field, or the net electric field at this particular point, will end up being to the right with some significant magnitude. Now, how do we figure out how long that arrow is? That is, what the magnitude of the electric field is there. Well, to find that out, we're going to take the magnitude of the electric field due to the positive charge and then subtract the magnitude of the electric field from the negative charge because it's in the opposite direction. To do that, we apply our formula, K Q over R squared for both. But it's important to recognize a few things, okay? This R right here is the distance between the point and that positive, this Q right here is the amount of charge for the positive charge, okay, to this point. Notice that that is the same value as the 1.5 nanocoulombs in the negative electric field component, although if you wanted to, you could have added these two fields and recognized that this was a negative charge, okay? And you notice that's equivalent here to simply subtracting the two fields. The other important thing to recognize is that the positive charge is 0.012 meters away, and the negative charge is 0.024 meters away. Okay, so you add them up, you plug in the formula, and that gives you a magnitude of 7 times 10 to the 4th newtons per coulomb to the right. The second problem I'm going to look at is this one, and I'm just going to sketch the solution here. This is the most complicated problem you might be expected to solve in the IB, and in fact is probably a little more complicated than I would expect on an actual exam, just given the amount of time it would take to solve it. So here's the setup. Again, you have a dipole. Q2 is positive 50 microcoulombs. Q1 is negative 50 microcoulombs. And you're asked to find the electric field in two spots, one at B and one at A. Now, the electric field at B is in some ways a little easier. Why? Because as discussed in the previous video, directly along the line connecting the positive and the negative charges, you get some nice symmetry. The electric field from the positive charge is up and to the right, and the electric field from the negative charge is down and to the right, but they have the same magnitude because they're the same distance away from point B, and they are the same magnitude of charge to begin with. And what that means is that the length of this arrow, that net electric field at B, will be only the horizontal component of one of those electric field vectors times 2. Notice the vertical component will cancel out. So in the calculation in part B here, okay, it's actually the magnitude of that net electric field is 2 times the horizontal component of one of the electric field vectors, EB1 or EB2. Both are equivalent. You calculate EB1 and EB2 using that electric field due to a point charge formula, KQ over R squared. Q is the magnitude of the charge, 15 microcoulombs. R squared is the distance away to the charge. Notice it's the same, okay, in this particular setup. It's the same distance, 40 centimeters, to both charges. And you multiply by K. That gives you this magnitude. Then to find the magnitude of the electric field vector at B, you simply double that horizontal component, which is shown here. A is trickier. A is probably the most annoying kind of problem you'd be given. The electric field at A is due to two components, the electric field from Q2 and the electric field from Q1. The electric field from Q2, because it's the force that would be felt on a small positive test charge, is up and sort of directly away from Q2. It's vertical. And the electric field contributed by Q1 is towards Q1 at an angle of 30 degrees as measured to the horizontal. Okay? And the key ingredient to calculate this, or this quantity, is to recognize that the net electric field is just the electric field component from the positive charge plus the vector sum of the electric field due to the negative charge. And that gives you a net electric field up and to the right. Notice it's slightly shorter than only the positive component, okay? More or less because it's being, so to speak, pulled down and to the right. Now, how do you get this algebraically? Well, algebraically, this is a particular value. We can plug that in to find KQ over R squared, and this is a particular value. Same deal. That is, so those calculations are shown here. Those both involve plugging in for K, for the correct Q, and then you have to attend to the correct distance. So the distance to the positive charge is 30 centimeters. The distance to the negative charge is 60 centimeters. Once you have these two magnitudes, okay, those are the magnitudes of EA1 and EA2, you can then figure out the magnitude of EA by observing that the magnitude of the vertical component of EA total will just be EA2 minus the vertical component of EA1, okay? And that's shown right here. EA2 minus the vertical component of EA1 found using trigonometry, right? That vertical component, so you're taking sine of 30, multiplying by the value of EA1. And the x component of EA is simply the horizontal component of EA1 because there is no horizontal component of EA2. Once you have those two values, EAX and EAY, you can use the Pythagorean theorem to get the total length of the vector EA. So 1.1 times 10 to the 6 newtons per coulomb squared plus 4.4 times 10 to the 6 newtons coulomb squared is equal to 4.5 times 10 to the 6 newtons per coulomb squared. And the direction you can then get by taking the ratio of the vertical component of EA that you just found to the horizontal component of EA that you just found. And that is shown here, giving an angle, phi, relative to the horizontal. Notice that's measured, shown in the diagram right there, of 76 degrees.